Good afternoon, everyone. Welcome to this afternoon's second session. Our speaker for this session is Fabrizio Zilibotti. Professor Zilibotti is now professor at Yale University. He has done a lot of work on growth and development. I'm going to cut short my introduction to Professor Zilibotti because whatever I say, well, it will be biased anyway because Professor Zilibotti was my PhD advisor. So please join me in giving a big hand to Professor Zilibotti.
Well, thank you very much for this kind invitation. And needless to say, much of the work I've done on China is with Michael, and this is also the basis of the presentation today, which also involves Michael Koenig and Kjetil Støre-Sletten. And this is a paper that tries to cast some light about what is currently happening, or what has happened in the last decade, perhaps more precisely, in China, about the transition towards an innovation-driven economy, which is one of the key words of the official rhetoric of the authorities in the last in the last few years. So there is the idea that now China has come sufficiently close to the technology frontier that it's about, in some sectors at least, to take the lead or becoming one of the key forces of the innovation process at the international level. Now, if one looks at the aggregate data, there is a remarkable change that supports this view. So the investment in R&D as a share of GDP for China has gone from 0.6% to 2%. So from the level of an emerging economy, typical level of an emerging economy, to the level of an OECD country. Still lower share than Germany, United States, and Japan, but it's a higher share than the United Kingdom or Italy and Spain, to mention some of the industrialized economies. If you look at the business enterprise expenditure, the picture is pretty much the same. So it's not just investment in basic research. So, of course, R&D is an input. The question somehow is, what's the output? There is a view that is quite common among many Western economists. My friend Darren Acemoglu, for instance, has written about that, that somehow the institutional setup of China is too much of a hurdle for China really to become a leading, innovating nation. So here is a quote from a study published by Harvard Business Review that summarizes this view. So somehow the Chinese government, according to this view, would be very capable to promote large top-down projects, but when it comes to diffuse innovation, there is a need of more bottom-up approach that the institutions of China would not be, this view says, appropriate for. Well, so we decide to look at the data and try to get some insight from that. And then this is the presentation of today. It will be a model that disciplines our reading of the data and the data themselves. The first picture actually we looked at was somehow encouraging to the view that R&D is having at least some effect on productivity growth. Let me describe this graph because I will show many graphs with the same structure. So here we take the universe of Chinese firms above a certain threshold of size, and we break down by their TFP percentiles. So what we see in this particular graph is the annualized TFP growth between 2001 and 2007. It's broken down in two dimensions. One is by percentiles of TFP, and many graphs will have that structure, so bear that in mind, and whether or not they do R&D in 2001. So you see that, at least qualitatively at this stage, there is evidence that firms doing R&D experience higher productivity growth. Of course, the question is by how much, and to what extent this process is efficient. There is no cost side, for instance, here. Okay, so this is the first question I want to address today. And the second is whether the allocation of R&D investment is efficient. So there is a growing literature in growth and macroeconomics that emphasize the role of distortion and wedges at various levels. Influential work of Xie and Clino, among others, have shown that this may be one of the important key element to understand the differential development across nations. That, those studies typically take productivity as given and then look at misallocation of factors. So somehow one of the contributions of what I will show today, although today I will try to stay focused on China, is to have a kind of step ahead in that way of thinking that also introduces the notion of allocation and misallocation of investment in innovation as measured by R&D investment. Now, there are good reasons to think that in China distortions may be important. We know that they are pervasive as a result of the important role of state-owned enterprise in that economy that continue to receive a significant degree of support from the government. In earlier studies, we have emphasized the role of credit market friction. Michael and Chiang Tai-shek have also worked on that more recently. And we know that there is a lot of action on the side of subsidizing R&D, creating incentive for industrial parks and so on and so forth. So the question we would like to get in the end is whether misallocation is important also in the quantitative sense. This is just motivating evidence. It's taken from another independent studies that actually documents that there are very important, the study by Chen Liu, Schwarz-Tarato, and Xu, that there are very important effects of the actual legislation that provides subsidies. So for instance, until 2008, some subsidies could be cashed if R&D intensity was at least 5% of the total value added, and that gave rise to a significant spike at 5%. Then if you go to different years, they change the legislation, and you see the spike that moves along with the legislation, suggesting that there is something like making up statistics or creating some in a more or less imaginative way some R&D. So that's of course only a suspicion at this stage. So how do we benchmark China? Well, we decided that something sensible would be to compare it with an economy that has many similarities. In fact, depending on different parts of views of the world, could be or not part of China, something I don't want to discuss. So China, we want to compare it with Taiwan. Taiwan is a much more technologically advanced economy on average than Taiwan. We're going to look at Taiwan a few years back the road. And we are also trying to use a model to tell us how important, in a quantitative sense, this misallocation can be for economic growth. So in the rest of the presentation today, I'm going to first lay out some facts on R&D in a comparative way, looking at China and Taiwan at the same way on similar statistics. I'm going to present a theoretical model that is motivated by those facts, and then I'm going to estimate the models and also show the result of some counterfactual. So I'm gonna state 5 stylized facts. The first stylized fact is that the growth rate for firms that do no R&D. So I'm going to take the view that, I'm going to look mostly at the extensive margin. So I'm not going to focus much on how much R&D firms do, but rather whether firms do or do not do R&D. Our insight we have from the data is that much of what I'm going to say also holds on the intensive margin, but the focus here will be on the extensive margin. So I'm going to take the firms that do not do R&D, and I'm going to plot, this is the plot I showed you yesterday, Sorry. The time zone confuses me a lot, you see. 5 minutes ago. And you see that the TFP growth is declining. Now, we suspect that for firms at a low level of TFP, there is also a lot of survivor bias effect. We think that this probably, is less important for higher TFP percentiles. So there may be some effect that low productivity firms exit in large numbers if they are really not doing well, if you have a permanently low TFP realization. So that may explain why the firms that survive have so high TFP growth. But this is quite consistent across all the percentiles of TFP. And this is one of these forces that keeps together the distribution of TFP productivity. Otherwise, we would see an ever-growing dispersion, which we don't see. This picture is broadly similar between the two countries. The second fact that I have already hinted for China, but I want now to especially emphasize the comparison with Taiwan, is that R&D firms grow faster than non-R&D firms. The gap is growing in the TFP level, so it's particularly true for firms that are high productivity to begin with. And in Taiwan, this gap is much larger than for China. In fact, when you compare Taiwan and China on the same scale, the nice graph I showed you before, it almost looks like in China there is not a significant difference in performance between R&D and non-R&D firms. There is a difference, but it's much smaller than for Taiwan. And especially for Taiwan, when you go to high productivity firm, the gap is really high. Whereas for China, it grows a little bit, but not so much. Fact number 4, the probability that a firm engages in R&D, it's strictly increasing in TFP. But once again, the trait is stronger in Taiwan than in China. I will come later. How do I take care of this? So I will come later to tell you what data exactly we're looking at. So bear with me if I take this order. But somehow in our sample for Taiwan, which is from data from the 90s versus China, you see that first of all, on average, Taiwanese firms are more likely to do R&D, but especially so for high productivity firms. In China, the profile is increasing, but flatter. And the last fact is that firm revenue is positively correlated with R&D, and in this respect, the pattern is similar. Once again, somewhat steeper for Taiwan than for China, but not terribly different. So these are 5 facts that we would like a theory of R&D investment and then R&D misallocation we would like to be consistent with. So all in all, similarity, qualitative similarity between Taiwan and China. Quantitatively, everything looks somehow sharper for Taiwan. So I'm going to present a theory with the following building blocks. I will not, for this presentation, take you through the math, but somehow if you want to have some idea more formal, the recent paper by Koenig, Lorenz, and myself on theoretical economics contains the basic ingredients. The model I'm discussing today is a generalization, if you like, of that. It's a model where firms can improve their productivity by two activities, by innovation and by imitation. Here the idea goes back to the previous work I did with Acemoglu and Aguillon. We think of R&D as a proxy for investment in innovation. So we think of firms that do R&D as being more intensively trying to innovate and move the frontier rather than simply adopting technologies in place elsewhere. We take the view, at least in the empirical work, that the distance to the local frontier is what determines the imitation success rate. So firms that are behind the frontier can improve their productivity by being matched with firms that are ahead in the productivity distribution and adopting those technologies. But which productivity distribution? Well, here we are thinking of the productivity distribution within China. Of course, there is also a question of whether these firms actually adopt technologies directly from abroad. If they adopt it from abroad, it's because these firms have already invested in China or Taiwan. We will introduce, relative to the KLZ paper, sources of heterogeneity that will be important both in the estimation and the interpretation of the result. And we will obtain prediction about which firms do R&D and how fast they grow. So the model has a static and a dynamic component. The static component is essentially a version of Schoen-Klenow QJ 2009, where each good is produced by a monopolist of different sectors that aggregate in a particular way. There are capital and labor markets are competitive and distorted, and we focus on a notion of output wedge, which is a combination of tax and subsidies on capital and labor. In principle, we could distinguish between a capital wedge and the labor wedge, which we actually plan to do it. For the result I'm showing today, it doesn't really make a big difference. So it keeps it more compact. So for those of you who are familiar with that theory, for the others, I just take it as useful information. Well, you can use the data to identify the output wedge and the productivity by having data on the sales at the level of each firms, on the expenditure on capital, and on the wage bill. So essentially, if a firm has very high sales, it could be for two reasons. It could be because they have a high TFP, so they are very productive, or because they are helped by some type of, by the subsidies of the government, for instance. So once you control for the level of TFP, when you see a firm that has a high sales, you think that firm is a darling of the government. So this allows us to retrieve those wedges and the productivities, again, in the fashion of Schoen-Klenow. Just note that the profit of a firm, is quite intuitive, is increasing in both subsidies and productivity. Here, now one detail about the model. We are using an OLG structure, which simplifies, it's not strictly essential for what we do, but it simplifies a lot the analysis and also the estimation process. So we assume that people live for 2 periods and that firms are transmitted from parents to children, again, building on our previous work. And so there are these young entrepreneurs that inherit the parents' TFP firms. They decide how to improve their productivity, and that generates some profit in the next period. In a more general model, it would be the entire present discounted value of future profits, which, however, in turn will depend on the productivity, on the evolution of the productivity distribution in the whole country. So that will be a bit more involved. And here we take this shortcut that allows us to focus on R&D decisions that only depend on the current productivity distribution. Okay, so now let's look at the dynamic part. There are first productivity, as I said, can be increased via innovation or imitation. We assume actually that, again, in the spirit of simplifying the more general model that I mentioned before, we assume that there is the step of the improvement is given. So you either improve along the quality ladder or not. You could have a generalization in which also the size of the improvement is endogenized, like we have in the TE paper. And then, so the key choice is a binary choice. A firm can either actively imitate or innovate. They cannot do both at the same time in a qualified sense that I'll show you in a moment. So active imitation entails no cost. And the firm is supposed to go out and be matched with a random firm in the outside productivity distribution. And then if it finds a firm that is more productive, with probability Q, will be able to learn and to improve its productivity. So this type of modeling and many possible generalizations of this would generate an advantage for those who are behind, because there are more firms from which they can actually imitate. And imitation can be successful, can lead to failure. The alternative to that is innovation. Innovation instead entails a cost. There has to be an investment cost that has to be paid, which is proportional to the average productivity for the model to have balanced growth properties. And there will be success with probability P, failure with probability 1 minus P. And we assume that if there is failure, there is still some lower probability that the firm can learn from and imitating from other firms. So imitation can come if innovation fails, but less effectively than for a firm that is just working on imitating. So let me show you graphically what this means. So this is the expected productivity growth conditional on TFP. And there is a threshold. Suppose that there is no cost, like in our earlier paper. Well, then just you compare the expected productivity growth from imitating or innovating. And because imitation is more effective when you are far from the frontier than if you are small, then there is a threshold. And all firms that have a higher productivity innovate. Those with lower productivity imitate. When you have a cost, well, it's similar, except that one has to take into account that there is the cost. So the threshold relative to the previous case will be farther to the right. The important thing is that when there are wedges, for instance, suppose that there is an output tax, well, that output tax is going to reduce the incentive for firms to do to do innovation. So more firms will actually do imitation. And the opposite if you have a subsidy. So a firm that is subject to subsidy to output will be more likely to try to innovate. Okay, so then we have a model of where the productivity dynamics, the distribution of productivity dynamics, given some initial condition, evolves over time, and the model keeps track of that. And graphically, this is what happens. What we show is, for firms that are sufficiently far behind, there is a higher probability to make progress. Then imitation becomes less and less effective as you approach frontier. At some point, firms that are sufficiently high in productivity will do innovation, and innovation will also push ahead the frontier. So the frontier will be pushed ahead by innovation, and imitation will make sure that everyone follows up. And what we can prove is that this process generates a stationary distribution, which we call it a traveling wave. This relates to the work other people like Benabib, Perla Antonetti, or Lucas and Moll in different contexts. It's a model of endogenous evolution of the productivity distribution. Now, I want to emphasize the role of wedges here. So if you have an economy without any distortion, like in the theoretical paper I mentioned, well, there is a threshold that is the same for every firm. So we should see all firms below a certain threshold doing imitation, and all firms above the threshold doing R&D. Well, when you have wedges, the picture becomes smoothened. So if you have a distribution of wedges, then you would see that there is still some correlation, but how strong that correlation is hinges on the extent of the distortion. So at the point that if those distortions are massive, we would have almost an independence of the decision whether to invest in R&D on the level of TFP. Okay, so this is the model that we are using and taking to the data. I didn't go through the math, but we'll try to explain what all parameters are. So what data are we using? We use data from industrial firm survey surveys for China and Taiwan. These are essentially census data that I'm sure here most people are familiar with. The data for Taiwan are a little earlier, are from 1999, 2004. It's a balanced panel with 11,000 firms. The data for China are from 2001 to 2007, and we plan also to have the 2007-2012, which is subject to some data issues that I will not have the time to discuss. So today, I only look at this period. It's a panel with 78,000 firms. We look at balanced panels. And the idea is we estimate the model on Taiwan, And under the assumption that we will discuss, that the technology for R&D is the same across the two countries, as a kind of benchmark maintained assumption, I want to see what happens if I feed the estimates of Taiwan into China and see then how the model performs and what type of distortion, if anything, it allows me to identify relative to Taiwan, not relative to an ideal first best, where probably no country is. So it's again similar in spirit to Schenklinov when they look at China and India and compare it to the US as a benchmark. Okay, so all the analysis will be based on data after removing industry fixed effect, including the data that I've already shown you. So somehow there are, what I show you may depend on many other things, but not on composition effect, on China becoming more relying on electronics and less on textiles. So under some assumption, at least, this should be controlled. How do we go about this? First step, we infer the wedges and the TFP from the data. For each firm, we take the data and we infer, the way I mentioned before, following Schenklinov, the extent of this static wedge, if I allow me to call it that way, because there will be other wedges later, and the productivity. Next, we derive some moment from the data. In particular, we're going to estimate a number of statistics, sorting them by TFP. So in the spirit of the pictures I've shown you at the beginning, I'm going to show you, actually the graphs are essentially the same, but I'm going to use those as the target of the estimation. For in particular, to remind you, because this was at the beginning of the talk, although it's not yesterday, some time has gone, the TFP percentile, for each TFP percentile, I'm going to show you the probability that the firms does R&D, the TFP growth conditional on not doing R&D, and the TFP growth conditional on doing R&D, or more precisely, the difference in TFP growth between firms that do R&D and don't do R&D. And I'm going to do the same by sorting by sales revenue and showing you the probability of doing R&D. So the first graph here, this is Taiwan. These are exactly the same graph you have seen before, but I'm compacting the picture for Taiwan. So this is, by bootstrap, I show you also the standard errors. This is the probability that a firm does R&D as a function of the TFP level. The probability that the firm does R&D as a function of its revenue. The TFP growth conditional not doing R&D, and the difference between firms doing and not doing R&D. And this is the same picture for China. Then we estimate the model by simulated methods of moment. And we do it on Taiwanese data. So we trim the bottom 10% of TFP distribution. Well, first of all, it doesn't really matter much, so the results are robust. Not fully so. So the fit for the low 10% is less good, because you remember that there is, for instance, a very high productivity growth for those firms that we suspect that it's related to the survival bias. But again, if I include that 10%, although I have a less good fit at the lower end, the results are otherwise not very different. And then we estimate 4 parameters. So first, I'm going to estimate the probability of success for innovation. Remember, if a firm does innovation, then there is a probability that this firm succeeds. I'm going to allow for some heterogeneity there, and I'm going to take a uniform distribution truncated at some p-bar, and that's the parameter I estimate. So I assume that at the beginning of the period, each firm realizes if it's good time or bad time for doing R&D. So some firms will understand it's not good to do R&D. Some firms will understand it's promising, and then they will go for that. Well, I need to have some assumption of that sort, because not that many firms, neither in Taiwan nor in China, do R&D. So that allows me also to match quantitatively well the model. I'm going to retrieve the imitation parameter. This is the probability that imitation is successful, conditional on meeting a more productive firm. I'm going to estimate the passive imitation parameters. You remember the innovating firm that fail to innovate, they still have a chance to imitate, but with a lower probability. So that delta will be typically a number smaller than 1. And then I'm going to estimate a distribution of costs of doing R&D. I'm assuming normality, and I'm estimating the mean and the variance of that process. We're going to target 16 moments in the particular picture I've shown you. In principle, I could take 1 moment for every percentile, or 4 moments for every percentile. At the moment, we have only taken particular percentiles and target to that. But again, that's mostly a computational issue. Okay, so this is the fit of the model for Taiwan. So the blue is the fit of the model, and the black is the data. So you see that the model, at least to our relative to our prior, fits not perfectly but relatively well the data. It can generate an increasing profile of R&D to TFP, so probability of doing R&D. It also generates this positive profile, which is related to the given the estimates of TFP, this is related to the wedges that we retrieve from the data. So that comes from the data. What doesn't come from the data is the distribution of C. That instead is estimated. Is estimated when we estimate the model. This is estimated before, so we just take it from the firm level data. We get the distribution of wedges. We fit pretty well the TFP growth profile for firms that do no R&D, and with some error at the lower level, the TFP growth difference between R&D and no R&D firms. Recall that our model has as one of its core prediction that firms with high TFP level have a comparative advantage in doing R&D. So that's where this increasing profile comes, because those are the firms that should do R&D in an efficient benchmark, and this is what you see. Okay, so now let's take Taiwan and go to China. And let me start. Of course, I could re-estimate the whole thing, and I will tell you, if I have the time, what happens. Of course, first let me tell you this exercise. So I want to think like we do in the development accounting literature, that there are not technological differences across country, and see how far I can go. So suppose that I have the same parameters, but I impose the Chinese tax wedges, and I allow myself one exception to this rule. I re-estimate the average R&D cost. Because on average, there are fewer firms doing R&D in China than in Taiwan in that period. Otherwise, you would just see that it's wrong in level. So I'm assuming that there is one difference, but just in the level of R&D cost. And for some reason you don't like that, you will see simply a shift in level, which is not what I want to emphasize anyway. Well, here is what happens if I feed China with Taiwan. There are a lot of differences. Now the fit is far less good. First of all, the model predicts far more selection by TFP than we observe in the data. It looks that it's too infrequent the case that the best Chinese firms do R&D, and too many of the not so good Chinese firms actually do R&D. Second, well, even the selection by revenue percentile is stronger according to the model, according to the data. Sorry, according to the model than according to the data. And most interesting, perhaps, the model predicts larger productivity growth for R&D firms than in the data. So the model does not understand why the growth effect, or the productivity growth effect for Chinese firms is so small relative to what we observe in Taiwan. So it looks as if R&D is significantly less productive, especially so for high productivity firms. Okay, so there may be many reasons for that. Let me try some candidates. First, it could be that there is more scrambling in the cost of R&D. So suppose that the government randomly give away subsidies, which results in a wider and wilder, perhaps, distribution of cost of doing R&D, then we would have probably a model that generates more random allocation of R&D decision. The second candidate is that actually Chinese firms are not so good at doing R&D. They have worse prospects. So the parameter P bar, the probability of success of our R&D, the distribution parameter on the uniform is smaller. So firms are intrinsically less good. And I'll show you that neither of these two fixes the problem. And I'm going to suggest my preferred third solution, which is moral hazard. Okay, what if I scramble by allowing an increase in the variance of C? Well, somehow the model asked for that because it asked for a much broader, a much more dispersed distribution of cost of R&D. It fixes to some extent, not perfectly, panel A. It doesn't do anything to panel D. So panel D continues to be a problem because it's true that some firms that should do R&D don't do R&D, but still the firms that are most productive and that do R&D should do much better than those who don't do R&D. That's what a model with a larger support of this type of R&D wedges, if you want to call it that way, would predict. So this model does not fix one of the two main failures and only fix partially the other. Now, what if Chinese firms are less talented for doing R&D? Well, it does not work. This I am only allowing the lower P bar, but even if I combine the two, not much happens. And again, I continue to get the wrong picture here. So the model continues not to understand why those Chinese firms that in spite of all distortion do R&D and are highly productive don't do much better than they actually do in the data. So let me try a model where there is moral hazard in R&D. What do I mean by moral hazard in R&D? Well, suppose that there is a dispersion of costs in R&D, which is different possibly from the one of Taiwan. But that's I have already done in the first exercise. But I'm thinking that these tax and subsidies in China are subject to an additional level of manipulation. So I'm thinking that some firms could actually cash in those subsidies, show up R&D in the data, but not actually do R&D. That's the new degree of freedom I'm giving to the model. So firms can fake R&D, they can cash a subsidy, and instead they behave as business as usual. They tell the government, yes, I'm doing R&D, they are invited to the technological part, they cash in the subsidies, but they do nothing. So they just pay perhaps some useless costs or relabel some of the costs. So note that the candidates which firms will especially be interested in that, are those who don't have a great perspective for doing R&D, or firms that are received a large subsidies. For instance, if a local government in China is setting up a very attractive technological park and gives an epsilon very high, well then firms will have an interest in being invited and be there. I'm going to allow these subsidies to be correlated with the other subsidies, the output subsidies, and the TFP. This actually follows, in a crude way perhaps, but the nature of the way these benefits are dispensed in China, which is related to the level of productivity to some extent. And also, this is more speculative, but perhaps not so much, and the data anyway suggests that that is the case. Firms that are the darling of the government or some local government on the output side, they are more likely to be also the darling of the government from being invited to these technology parks. Well, just one intermediary piece of evidence. This is nothing from the model. I just want to, we run some regression, and for instance, it is the case that if a firm is in state-owned enterprises, conditional on all the other characteristics of these firms, it's much more likely to do R&D. So this is a first indication that this type of distortion are there. The paper by Daniel Xu and co-authors I showed before is a more careful and detailed description of that. Okay, so here is how the model fits for China once I allow to re-estimation with the characteristics I told you. So there is this moral hazard problem, and I allow this type of targeted subsidies to be correlated with productivity and with the output subsidy. Well, now the model fits pretty well in the sense that I've significantly flattened the profile. There are many firms that should not do R&D, but because of these somehow ill-devised subsidies happen to do R&D at the low level, and at the high level some firms are instead taxed. This is similar to experiment 1, if you like, but the most important thing is that I get not a perfect but a much better fit for number 4. So now I have also an explanation for why firms that have a higher TFP to begin with, that are better placed to do R&D. If they do R&D, they don't do so well. And what is the solution of this puzzle? Well, here I'm showing you the red schedule is the distribution of firms that actually do R&D. So this is those who declare to do R&D. This is those that actually do R&D. So, for instance, and let me focus especially on this because my time is going. If I look at this picture, it turns out that the firms that are actually do R&D, the kind of Huawei type, they are very productive. The problem is that they get confounded in the data with many firms that actually fake R&D. And the same explains here the reality, according to this estimation that, I repeat, is based on the assumption that the other technological parameters are the same in Taiwan and in China, which may not be true, of course. But under those assumptions, the amount of R&D that is done in China is significantly lower than the one we see in the data. Because the gap between the red and the blue line is explained by fake R&D. So firms that cash in the R&D and they don't do anything productive. Of course, the model does it in a crude binary way. We could think that they do a little of R&D or that they do projects that are not really productive. So it's a mixture of firms getting subsidies and running R&D when they are not really good at that, and also firms that cash in the subsidies and they don't do R&D at all. The two things together reconcile the model of China with the one Taiwan. Of course, an alternative would be to re-estimate the model for China. What I would get if I do that is that the productivity of R&D in China is desperately low, so there is very little effect of it. If you want, under the maintained assumption that there are some commonality in the technology, this gives a micro-foundation to that result, or at least a candidate explanation. Okay, so how important are these effects on aggregate? This, I must emphasize, is the most preliminary part of our work, so I hesitated. And the result, I hesitated to show it, but I prefer to do it. So the results on aggregate are not very large, according to this model. So funny enough, because in this model there are these effects from imitation, so the firms that don't do R&D, the firms that don't actually do R&D still imitate. Well, the result on TFT growth are not huge, they are not insignificant either. They range between 0.8 and 1.4 percentage points. Now, in this period, productivity growth was very high, so that might well be in the order of 1/10 of the total effect. Which is, I think it's interesting. It suggests that at least with the lens of this model, the aggregate effect of this of this misallocation may not be huge. And with this, I conclude. I've documented evidence on firm-level distribution of R&D and growth in manufacturing industries in China and in Taiwan. I have developed a theory of innovation driven by R&D, imitation, and growth, which is consistent with those stylized facts, and that can gives us some new insights about misallocation of R&D that I hope it can be taken also beyond China in somehow giving an extra tool to people working on misallocation in models a la Xie and Clino. We estimated the model using firm-level data from Taiwan and China, and we evaluated some counterfactual. This is, of course, there are many more things that we could do in terms of counterfactual and robustness, but these first results suggest that there are important distortions in China relative to Taiwan, that the actual measure of R&D that we have may exaggerate the extent to which China is turning into an innovation-driven economy. We have used Taiwan as a benchmark because of the quality of the data. For many countries, for instance, using the US, typically people use CompuStat, but this is a very selected sample of firms. We want to have more census type of data. We are collecting data for Norway to see how it looks also in a Western economy. Thank you.
Thanks a lot. Since we started this session 10 minutes behind the schedule, let's take questions in the coffee break. Thanks a lot.